Nice.
Okay, great.
All right, cool. Yep, hi everyone. Yep, I'm Jack. This is work done by myself and Sam Staton. Yeah. Oh, cool. Yeah, basically to give you the context of where we'll be during this talk. Yeah, we're in probabilistic programming, but in particular for world modeling. Here our programs have some kind of commands to talk about uncertainty, and we use them to basically have programs which describe like world phenomena, and then we can automatically perform inference in order to get some kind of statistical analysis. Yeah, this has seen successes in, say, like with the UK in order to predict the spread of COVID. So what we did in particular with probabilistic programming is we wanted to give a fully compositional account which combines both Bernoulli uncertainty with Knightian uncertainty. So what Bernoulli uncertainty is basically regular probabilistic uncertainty, where say you have two outcomes, say we have an urn with a red and a blue ball, and yeah, we pick a ball basically probabilistically from the urn, so we have equal odds chance between a red ball happening and a blue ball happening. Knightian uncertainty is a bit more of an epistemic uncertainty, where we can think of this as the urn on the right, where we know there's red and blue balls in the urn. We know that the urn is non-empty, but we have no idea what the distribution of balls or how many balls are in the urn. So we'll pick a ball out of it, and all we can really talk about is what the possible set of outcomes will be. We have no prior on what the distribution is. So the way we usually talk about this is via non-determinism. And then these two types of uncertainty together is what we call imprecise probability. So the way we actually did this in a programming language is we named the Knightian choices and managed this using graded monads. And we showed two things about the model we produced, is that they actually give a refined bound on the uncertainty compared to previous models. And it's basically the furthest we could push this kind of idea, because if we tried to push it any further, something will break, which I'll make clearer later. Yeah, so to give credit where credit is due, there's been a lot of interest, wider interest in probability and non-determinism and combinations of them. Some of them are here, but we are currently looking at the setting of imprecise probability, which is new and independent from all this. So yeah, let's first start off with to get an idea, a feel of what imprecise probability actually is. So if we take the Bayesian account of probability, we can think of basically a probability being the fair bet you would make given some kind of distribution or some kind of uncertainty about a world model. So we can think of this as, say, if we have three outputs from a system, say red, green, and blue, we can think of this as basically being a point in the simplex between these three outputs, which in this case is a triangle. So we can think of the point basically at red, so in this top left triangle here, the very top point, that basically represents 100% chance of red happening. The point halfway between green and blue, so P here, that basically represents equal odds chance between green and blue and impossibility of red. And then the point Q represents equal odd chance of everything. Imprecise probability is where we're now saying, okay, some of our probability or some of our uncertainty is no longer probabilistic. We don't know the distribution of it anymore. We just know the set of possible outcomes. And so instead of having a single fair bet that we could make, we have a set of possible bets that we could make based on the situation. It turns out this set will be convex in order to just be consistent with a regular world model, which goes down into the philosophy. But the way we could think of this in the triangle in the top right here is if we say, okay, in one situation, there's a 100% chance of red happening, and in another situation, there is an equal odd chance between green and blue happening. But then there is some kind of Knightian uncertainty which dictates between one of these two situations happening. And then this will be represented by the convex set between this point of 100% red happening and the point between equal odds green and blue, because the Knightian uncertainty is saying, okay, we don't know what the distribution is, so it could be anywhere between certainty of red, or certainty of the first situation, certainty of the second situation, or some kind of distribution between them. So yeah, imprecise probability has had a number of applications in statistics, economics, and engineering. It's recently popped up quite a bit in machine learning, which prompted us to look at it, say in conformal prediction and AI alignment. But yeah, to get into the guts of it, our first language for imprecise probability, we're going to start with just a few simple constructs. So we're going to have if then else statements, so basically a way to condition on booleans and continue with one program if it's true and one program if it's false. We're going to have let bindings, so we run a program T, bind the value to x, and then continue with U, which may or may not reference x. And then we're going to have two commands which induce the two uncertainties that we have. So we have Bernoulli, which we can think of as a fair Bernoulli trial. So we have an urn with a red ball and a blue ball in it. And basically, when we call this command, we're going to randomly sample from the urn. If it's red, we return true. If it's blue, we return false. And then we have a command night, which we can think of as given an urn on the right, which we know is not empty and has red and blue balls, but we have no idea what the distribution is. So when we call this command, we pick a ball out. If it's red, we return true. If it's blue, we return false. But yeah, we don't know what the distribution on this is. And we get a new urn each time we recall this command, so there's no way to figure out or to slowly converge on what the actual distribution of the urns are. So yeah, how can we actually start talking about imprecise probabilities with this language? So to just give you a few examples or a feel for what we'll be talking about, yeah, we can start with a very simple program in this language, which is the top left one here, where we sample from a Bernoulli, or we do a Bernoulli choice, and then based on that choice, we return green or blue. So because there's no Knightian uncertainty, we just have a single point. Yeah, there's no convex sets to worry about. And yeah, it is exactly the point, which is halfway between green and blue because it's a fair trial. If we increase complexity a little bit, so now we have one Knightian choice, and based on what the result of the Bernoulli choice is, we will condition on the Knightian choice and return red, green, or blue in this second logic here, in the top right, sorry. The way we can interpret this program as this actual convex set or imprecise probability is we can look at the two extreme values of the Knightian choice. So on one hand, x is going to be certainly true. And if this is the case, it doesn't matter what z is, we will get red with 100% certainty. On the other hand, x is certainly false. And in this case, we'll get 50% chance green and 50% chance blue based on the Bernoulli trial. And because x can be any convex set of these extreme, I guess, distributions, we get the convex set between this certainty of red and equal odds green and blue. And then we can increase complexity a little bit more, where we have the same program, but now we choose two Knightian choices, and the only difference is we condition on a different Knightian choice in the second branch. And now, because the Knightian choices are decoupled, we can look at the four extreme values given by the permutations of certainty of true attached to x, certainty of false attached to x, certainty of true attached to y, certainty of false attached to y. And these give us the four extreme values in this diamond here. And that's, yeah, generates, so yeah, these convex sets of probabilities. So what kind of properties do we actually want our language to hold? Well, given we're talking about languages which actually model probabilistic programs for real-world modeling, first of all, we want our language to be commutative. So if we have two programs T and U, which don't reference each other, return values which are attached to x and y, and then we continue with V, which does some logic on x and y, then it shouldn't matter if we run T first or if we run U first. So we can think of this as if we pull one ball out of an urn and then a second ball out of an urn without looking at either one, and then we look at them and do some logic, it should be the same as pulling the other ball out first and then that ball because they're completely independent. And same with, this is also the case with affinity. So if we pull a ball out of an urn, don't look at it, toss it away, and then continue with some program logic, well, basically it should be the same as never having pulled that ball out of the urn in the first place because, nothing in our program mattered on it. So this allows us to talk about our programs as data flow diagrams, which is very common in probabilistic programming for modeling. And the second piece of desirability we want is standard equational reasoning about if-then-else statements. So basically, if we do the same let binding in both branches of an if statement, because we're talking about world modeling, so only one of these branches will be executed, we should be able to hoist this let statement out of the if statement so long as it doesn't interact with B, because in both cases, the let statement will only be executed once. So what ends up being the actual problem? Well, one model that actually supports convex power sets of distributions is the convex power set monad. But the problem is it's actually not commutative. So we have this function down the bottom here, which we pass a Bernoulli value to x and a Knightian value to y. It actually matters which Bernoulli or Knightian value we sample first in the interpretation in the convex power set monad, and so it doesn't actually give us a reasonable account of imprecise probability. And in fact, no semantic model works because we have this paradoxical program here where we basically sample two 19 choices on each branch. And yeah, the paradox arises in whether they're the same 19 choice or whether they're different 19 choices. And in each interpretation, we get the left or right convex power set here. And yeah, and basically the desiderata basically says there's no way we can actually distinguish these. So there's no way to actually talk about imprecise probabilities in this semantic model. So the way we actually solve this is just to attach a label to the 19 choices. So in the first case here, we see we label both 19 choices with the same name, and therefore we get the convex power set where they're both correlated. And in the second one, we attach them with different names, and because now they're independent choices, we get the wider non-deterministic set of outcomes here. And we can no longer equate these two programs because we can no longer hoist the let statement out of the second program. So how do we give an actual semantic model for this? Well, the way we do this is via graded monads. So we take a reader monad transformer of the finite distributions monad. So you can think of the set A here as being the set of 19 choices, or the set of 19 names for the 19 choices we have. So 2 to the A is the set of all possible non-deterministic branches we can take. And so this reader monad is saying, OK, you give me one possible non-deterministic branch, and I'll give you the distribution, the resulting distribution based on that non-deterministic branch that you took. So we generalize this 2 to the A to arbitrary sets B, so talk about non-deterministic branches. And then we can actually recover the convex power set from this model by basically looking at the image of this function and taking the convex hull. And this is actually given to us by a canonical Khan extension, so it's a very natural way to go from one model to the other. So yeah, this is the, I guess, semi-formal definition. And this is how we actually interpret the Bernoulli commands and Knighting commands in our model. I won't go into the details here, but I guess the main point is that it was critical to use graded monads here because they give a way to semantically talk about error usage. And this meant we could actually keep track of which non-deterministic branches were assigned to, well, yeah, which non-deterministic branches were used in which parts of the program. And so when we compose programs together, either functionally or monoidally, we actually have a way to talk about how we bring these non-deterministic branches. And so, yeah, this is given to us by the graded monad multiplication. All right, so what did we actually show about this model? Well, the first one is that we actually get improved uncertainty bounds when we model within our framework. So we had this mapping where we take our monad and we take the image and it gives us a convex power set. In fact, this actually induces an oplax functor between the two Kleisli categories of the two monads. And what this means is basically if we compose programs in our framework and then map them across to the convex power set framework, we actually get refined bounds as opposed to when we map each program across individually and compose them together in that framework. And that's basically to do with we're keeping track of the non-deterministic branches, so we can do a little more about, we can talk, we have a little more refinement about how we use them. And secondly, it turns out there's kind of more stuff in our model than as opposed to the convex power set model, in that when we take this kind of mapping across, a few things get mapped to the same value. So we have more stuff in our model, which maybe we don't want because, yeah, it's strictly larger than what we actually want to talk about. So can we quotient it any further? And the answer turns out to be no, because we'll either break the connection with imprecise probability or we'll compromise the compositional structure. Yeah, so to just give a conclusion, what we did was use named Knightian choices, which we managed via graded monads to give a fully compositional account of Bernoulli uncertainty with Knightian uncertainty in a programming language. We showed this gave refined bound on uncertainty in our models. And it was also the best possible way, the best we could do with this methodology. For future work, yeah, we're interested in looking at iteration and infinite dimensional structures because currently we only support finitely generated convex power sets, but we'd like to support, yeah, larger ones. And yeah, looking at function spaces and of course implementation and inference with these with non-determinism is a non-trivial problem which we want to look at. Thank you.
Okay, so we have time for several questions. First over here in the second row. And is our last speaker in the room by the chance? Okay, great.
Well, because that's what you would expect when you're talking about world modeling, right? If you do two different, if you do two different samples which are independent from each other, then what I guess your language says versus what you're trying to model is different.
I think that's fairly probable.
Mm. Right. I mean, there's lots of, I guess, intuitions you could have between combinations of probability and non-determinism. So maybe the one you're talking about is a bit more like, yeah, the actual distributivity law, where you kind of have a more like demonic non-determinism, where it has all possible scenarios enumerated when you take that when you distribute one over the other. But here we're, I guess, less interested in that law, because we want to be able to talk about, these things commuting with each other. Because, when you plug, when you want to like plug these programs together, you don't want to have to worry about which program comes first and these sorts of things. You just want composition.
Okay, great. We probably have time for one more question.
Mm-hmm.
There are others who use interval-valued probability. So my question is whether the semantics that you have given, whether it is sensitive to how you represent imprecision.
Well, when you talk about interval-valued probability, that is also convex sets, right?
Yes, but what about ranges of probabilities?
Right, so we built our work based off, there is a big community of imprecise probability people who, there's like a book by Wally, which is seen as the Bible, and it has a very, the nice thing about this type of imprecise probability is there's a lot of different kind of angles you can view from it, and one is these convex power sets, but the other is these I guess it's more like philosophical views as coherent kind of bets you could make. We haven't really looked at, I guess, well, it depends what the other imprecise models are. I can't tell you whether it will work in those systems until, I know what the systems are. So, as in, yes, we give the semantics in convex sets, so yeah.
Okay, great. Thanks. We're right at time. Maybe we can continue these stimulating conversations afterwards. But let's thank our speaker and